All right. At the request of Keaton and bribery involving um, maybe some zebra cakes and or a donation to the Mays Solar Foundation, I'm going to give you a brief overview of kind of the highlights on the theory of relativity. Okay. So this was Einstein did his work early 1900s, and this is kind of the heady time of physics. This is when all the quantum mechanics stuff was going on, and then it eventually became into a huge deal. Like, how do you reconcile the theory of relativity and quantum mechanics? And that became like a whole nother issue as how to reconcile these two ideas. So Einstein was famous for his thought experiments. He was a patent clerk, and so he had a lot of time to think about because he was sitting there, at time. So what I want to do is kind of go through some of the big ideas that he had. So imagine this. So you've got, and he used trains a lot because that was kind of the big mode of transportation. So let's say, since Keaton really wanted this, so Keaton is on a train and he's going really, really fast, okay, in this direction. Now, over here, we've got Eric, okay? So Eric is standing here. He's just kind of chilling out. He's thinking about what to write on his wall. And he's seeing Keaton go by really, really fast in this direction. Now, there's a lightning storm going on. And don't get hung up on going, well, this can't happen. It's a thought experiment, okay? It's a thought experiment. So imagine, if you will, in this lightning storm, simultaneously, both of these telephone poles get struck by lightning at the exact same time, as observed by Eric. Okay? So Eric is staring at the wall and go, whoa, this is cool. Both of these got struck by lightning at the same time. Now, if you think about what has to happen, that light had to travel from this telephone pole to Eric and this telephone pole to Eric, and he's going to say, oh, since he's standing right between the two of them, he's going to say that these two got struck by lightning at the exact same time. So from Eric's stationary observation, both telephone poles got hit at the exact same time. Now, you're Keaton. Keaton's traveling pretty fast. So he's going in this direction, right? And since he's going in this direction, that light here he's going to be approaching this light. This light is going to have to catch up with him. So in Keaton's world, he's going to say this telephone pole here got hit before the one that was over here. So you have two identical explanations, and you can't tell the difference between the two. Because in Keaton's world, this one got hit first before this one over here. In Eric's world, they both got hit at the same time. So what's going to be important here is that you can have the same event taking place, but you can have different observations. Now, let's talk elevator. So let's say that you're in an elevator and you are in deep, deep space, okay? You're in deep space, so there is no effective gravitational field around you. So, you're standing here, okay? And you happen to have an apple, okay? You're in this elevator, you can't see outside, nothing. And you let go of that apple. Oh, Newton's first law of motion says, oh, that apple is just going to stay there and nothing's going to happen because there's no outside force to make it accelerate. It's just going to chill out just like you do. So you don't see the apple fall. Now, visualize this. Let's say that at the very instant that you let go of that apple, and this is going to be important, you have let go of the apple. As soon as you let go of that apple, the elevator is going to begin to accelerate upward. Okay? Now, here's Keaton, okay? All right? And here's Keegan out here. So Keegan is standing out here. Keaton is inside the elevator. So if you're Keaton, you're going to feel like you're in a gravitational field. You're going to feel heavy because your body wants to remain at rest. Now, Keaton can't see Keegan out here. Keaton can only know what's happening inside that elevator. So, according to Keaton, the apple is going to begin to fall, and he's going to experience a gravitational field. So, once this elevator begins to accelerate upward, as soon as he lets go of it, Keaton's going to see the apple fall to the floor, and he's going to feel a gravitational acceleration. Now, if you're Keegan, you have the same event happening, but you're going to view this thing differently. So if you're Keegan, you're going to see, oh, that's not what happened. You're going to see Keaton go up, and you're going to see the apple stay in place, and the elevator is going to come rushing up towards the apple. So if you're Keaton, oh, the apple falls. If you're Keegan, oh, the apple remains stationary, and the elevator moved up. So that's where this gets a little bit weird. So if you think of, you're in the kitchen and you drop an apple, well, if your kitchen is in an elevator and you can't see what's going on outside, you don't know if the apple fell or if the kitchen floor accelerated up towards the apple. Don't think about that too much. Bad things are going to happen. Now, to further complicate this, we'll get into this equation for time dilations later. I thought I moved it down far enough. I didn't. So visualize this. And this is one of Einstein's big ideas. We're back to the elevator, okay? Keaton's in here. And imagine that there is a hole in the side of the elevator. And we're going to shine a beam of light across here, okay? At eye level with Keaton. So if the elevator isn't accelerating, okay, this is going to be a key to this. If the elevator is just stationary, Keaton's going to see the light come in on this side and hit over here on that side. And he's going to say, oh, that beam of light went straight. Okay, that's cool. Now we're going to change it. Now we're going to take that same elevator. Keaton's going to be inside the elevator. We're going to shine the beam of light. Okay. Like this. Now, here's the key. As soon as the beam of light crosses this threshold, we're going to begin to accelerate this elevator upward. Okay? So, the beam of light, as soon as it crosses this threshold, we're going to accelerate the elevator upward. Now, what's going to happen, instead of hitting that point across here, depending upon how much acceleration that you have, that beam of light is actually going to hit down here. Now, again, this boils down to who's observing this. So if you're Keaton observing this, you're going to say, oh, this light is going to get curved because of the fact that it's going to hit at a point that's below this. So, but if you're outside, you're going to say, oh, no, that light went straight and the elevator moved up and that's why it hit below. Again, you have two completely different descriptions of the exact same event. But here's what's important, is that if you're Keaton, you're going to say that gravity is capable, or acceleration is capable of curving light. So this is going to be one of the big ideas out of Einstein, is that a strong gravitational field is capable of changing and curving light around a gravitational field, because that's what's happening, is that you're curving space and time. So that beam of light is just riding that curve of a beam of light. Now, so this is where Einstein gained rock star status. And I don't remember the exact details of this. I'm just going to paint you the big picture. This was, I think, in the early 1920s, as I recall. But there was going to be a complete solar eclipse, And so here's the sun. We'll get the sun yellow. Okay. Here's the sun. Okay. Ah, that was bad. Pretend that didn't happen. We'll go orange. There's the sun. Now, here's the Earth. And here's the Earth. And the moon is going to cross in between. And so we're going to have a solar eclipse. Now, back here, there was a star. And again, I don't remember the name of the star. Doesn't matter. But what Einstein predicted was that as that light was going to come around the sun was going to have a strong enough gravitational field that it was going to warp that light. And so this obviously only worked when you had a complete solar eclipse. Because if you don't have a solar eclipse, then you're looking at the sun and you can't see the star anyway. So this is why it was so important that these observations had to be made during a complete solar eclipse. So what Einstein predicted, and this is where you have to kind of understand optics. So when you're looking at it, you're here on Earth and you're looking at that star, it's actually going to appear to the left, because as the light comes around our sun, it creates a huge distortion in the gravitational field and it becomes warped. So then it's going to appear here. So what Einstein predicted, and this is how he got rock star status, is that he predicted exactly what that shift was going to be. Now, this was horribly difficult for the guys that were doing this. Some of them were like in, I don't know, like equatorial Africa, and this wasn't, oh, let's take a picture with your phone. I mean, this is when you had to have photographic plates and telescopes, and they had to drag all this stuff all the way around the world. And then when they got there, they hoped that the sun wasn't obscured by clouds or rain or something like that. Otherwise, you spent all of this time preparing for these expeditions. And again, this is before, you could hop on a plane and do this. You had to cruise on a ship. This was a huge ordeal. But what happened was that when they made that observation, it matched. That shift was exactly what Einstein had predicted. Einstein became a rock star. So, one of the genius things about Einstein, speaking of the sun, is that once they developed the capacity to measure the speed of light very precisely, which is tough to do because it's such a high velocity, for a long time they thought the speed of light was instantaneous. So what happened was that here's the Earth, and then you've got our resident star, and the light was going to go from the sun to the Earth. Okay? Now, the Earth, and this is looking down on top of the North Pole, is spinning in this direction. So, when they were trying to measure the sunlight, the speed of light from the sun, if you're on this side of the Earth, you're going away from the sun. If you're on this side of the Earth, because we spin counterclockwise. So if you're measuring, again, this is looking down on the top of the North Pole. So this would be like during sunset. So if you're in this position, this is recording the light as you're going away. This is recording the light going towards it. Okay? Away and towards it. Now, imagine, if you will, that we're going to take a car. Okay? Now, forget about this for just a second. And let's just do it on a fast skateboard. And so here is, here's Liza. Okay? All right? Flowing here. And she's going to throw a baseball towards me. And she's going to throw the ball at 10 miles per hour. And the skateboard is moving at 50 miles per hour. And so effectively, that's going to approach me at 60 miles per hour because of the fact that she's coming towards me. Now, if she is going away at, let's say, 5 miles per hour, and she throws it this way at 10 miles per hour, okay, then effectively that's a difference of like 5 miles per hour. So, depending upon whether you're moving or not, with Liza and the skateboard, I'm going to measure different speeds when I measure the speed of that baseball with my radar gun, if she's coming towards her or she's going away. So when they began to measure these velocities for the speed of light, what they realized is that no matter how they measured the speed of light, they always got the same velocity of the speed of light, 3.00 times 10 to the 8th meters per second. Now, they couldn't figure out what was wrong, because at the end of the day, they said, okay, this velocity is distance divided by time. So they got hung up on this side of the equation. They said, we should be getting different velocities. So they said, no matter what, the distance and the time are going to be the same. So therefore, we should get different velocities depending upon which side of the Earth we're measuring this from. Now, here's what Einstein did, and this was in sharp contrast to Galileo and Newton, who said that time is an absolute numeric value no matter what. Length is an absolute numeric value. Mass is an absolute numeric value. Whether you're on the Earth, on the moon, doesn't make any difference. Mass, a kilogram is a kilogram, a second is a second, a meter is a meter. So what Einstein did, and this is the beauty of what Einstein did, is that he accepted that the speed of light was a constant. He accepted this 3.00 times 10 to the 8th meters per second. So here's the genius of what he did. He said, I'm going to keep this side of the equation the same, which means that I've got to have changes in distance and time. Now, that screwed everybody up because of the fact that everybody perceived distance and time as being absolute numeric values. A meter is a meter, a second is a second, a kilogram is a kilogram. So this led into length and time and mass and energy dilations. So this is one of the big equations that came out of Einstein's work. And this led to what's known as the twins paradox. So in the twins paradox, you have one twin who is standing here on Earth, and then you have an identical twin, and there's variations on this theme. One of them, he's orbiting the Earth. The other one, he goes to a distant star in a spaceship traveling at like 0.6 the speed of light. Okay? So the short version of the twins paradox is that the twin who is traveling will age less than the twin who is on the Earth. So the faster you go, the more time slows down. So this is kind of like what's happening here. So this is like, let's say, for example, this is the time of the stationary observers. Call it 1,000 seconds, okay? Whatever that time is, it doesn't make any difference. So this is how fast you're moving, and this is the speed of light. Well, obviously, there's a couple of things that happen to this. If you're traveling at the speed of light, then you got the speed of light squared divided by the speed of light squared. You have time divided by 1. The two times are going to be the same if you're traveling at the speed of light, which isn't going to happen. But what's going to happen is this. So let's say that you're traveling at 0.6 the speed of light. So what's going to happen here is that you're going to have 1 minus a decimal, okay? Because you can't go faster than the speed of light. So you're going to have 1 minus a decimal. So you're going to have this 1,000 seconds divided by the square root of a number less than 1. So when you take this 1,000 and you divide it by a number less than 1, oh, look what happens. This time here then is going to be greater, and this is the time of someone who's moving. That time there is going to be different than that observed time. So the short version is that when someone is traveling at close to the speed of light, they are going to be in their frame of reference, and this gets weird in terms of how you're measuring time, but they've done this with atomic clocks. Like they put atomic clocks in orbit around the Earth that are very, very, very precise, and then they brought them back together. And then that clock that was orbiting, that time was running slower than the clock that was on Earth. Now, you obviously have to be going very, very fast. If this velocity is relatively small, okay, like for example, you're driving your car at 40 miles per hour. Well, that's such a small number relative to the speed of light that it basically becomes zero. So where it does get weird is if this is the speed of light, then you have 1 minus 1 and you divide by 0 and then it becomes undefined. So, but under normal circumstances, if this velocity is small compared to the speed of light, it's really not going to make any difference. Okay, so that's just kind of a brief overview of the theory of relativity. Keaton, I want my zebra cakes and or a donation to the solar fund. So anyway, hopefully this works. There's a whole bunch of stuff out there that kind of explains this some more. You can get into energy dilations, mass dilations, length dilations, time dilations. Faster things approach the speed of light, the more massive they become, which makes it harder and harder to accelerate it to the speed of light because the relativistic mass increases. So anyway, there's all that, kids. Hope you enjoyed it. Hopefully that piqued your interest. And